All right, this is homework 5, part 1. Water flows along an aqueduct with a width W inclined at an angle relative to the horizon at a volumetric flow rate of Q, assuming that the shear stress at the wetted wall to be equal to that of an equivalent circular pipe within the same average velocity. Drive an expression for the height h of the water flowing along the aqueduct. Write a Python code using scipy.optimize.root to solve for h when W is equal to 0.5, Q is equal to 1 meter squared, 1 meters cubed over seconds, when the aqueduct is inclined 15 degrees relative to the vertical. So we have our aqueduct here, pressure 1 at the top, pressure 2 at the bottom, and we're going to start with Bernoulli's equation. The first thing we're going to do with Bernoulli's equation, we are going to divide both sides by L and multiply both sides by rho, leaving us with minus P2 over L plus rho G delta Z over L equal to 4F over rho times V squared over D. And actually, let's chop this 4 down to a 2, just because we had this 2 over here. So we can see some things cancel here. We got, well, actually, first, before we discuss some cancels, let's talk about this P will cancel. Let's talk about this. This is actually going to go to 0. And this term is going to 0 because we have an open pipe and the pressure won't drop in an open pipe. So that's why that term is going to go to 0, just because it's open to the atmosphere at all times. So then we are left with G delta Z over L equals to 2F V squared over D. Now, let's talk about this delta Z term. We can rewrite this as L times sine of theta, because delta Z is basically just the change in length. And since we're at an incline at 15 degrees, it's just length times sine of theta, which is 15. And then that's over L equals to 2F V squared over D. So these L's are going to cancel here. So then we are left with G sine theta is equal to 2 F V squared over D. Now for a cylindrical pipe, we have water flowing down, and to get the how much water is flowing down, it's just the cross-sectional area times the length. If we multiply that by rho G, that is the weight times the length. So that is, we can equate that to the shear stress times the wetted parameter over the area. I'm sorry, just the wetted parameter times the length. Is a balance here. So the weight of the flow and how weight times the volume of the flow is equal to the shear stress times the wetted parameter times the length of the pipe. The wetted parameter is basically just what surface of how much of the water is in contact with the surface of the pipe. And these L's will cancel, and we can divide both sides by A, and we are left with rho G is equal to the shear stress times the wetted parameter over A. And for all equations, this term, wetted parameter over the area, is going to be equal to 4 times over the diameter of the pipe. So that leaves us with rho G is equal to 4 over D times tau. And we can put this into, and then we can divide both sides by rho. So we're left with G. So then we are left with G is equal to 4D over tau over rho. And we can actually throw this into G over here, which leaves us with tau over rho times 4 over D sine theta equal to 2 V squared over D. These D's will cancel. And if we solve for rho, we are left with quick math in my brain. Tau is equal to, this is going to go to the bottom, so that's, here, let's write this one line lower so we got space. Tau is equal to FV squared rho, yeah, over 2 sine theta. So that is the shear stress term. Now let's look at, let's work back here a little bit. For this pipe, let's talk about the wetted parameter of this pipe over the area. That is going to be equal to 2 times the height plus the width of the pipe, because we have 2 height parameters for what water is touching plus the width parameter, so that's why it's 2h plus w. And then over the cross-sectional area of the pipe, which is just going to be h times w. So we can plug this back into our equation up here and plug in tau, which we just found. So we can put all of this together, and we would be left with rho g is equal to tau, which is rho fv squared over 2 sine theta times 2h plus w over hw, and then these rows will cancel. So then we are left with G is equal to F times B squared over 2H plus W times 2 sine theta HW. Now, we know all of these parameters except for the velocity here, but we do know that velocity, let me go over here, velocity is equal to the cross-sectional, equal to the flow rate over the cross-sectional area. And we know that the cross-sectional area is equal to height times the width. So we can plug that in for V, which gives us our final equation of G is equal to friction factor times Q squared, flow rate squared, times 2H plus W, all over 2 times the sine of theta times HW cubed. There we are. That is our reduced equation that we're going to plug into Python. Now, before we go over to Python, we do need to talk about one more thing. We know that from our Churchill equation from part 3 of our homework, not part 3, homework 3, that is equal to the Reynolds number and the equivalent diameter. Those are the 2 parameters we need to know for the Churchill equation. So we know the Reynolds number. The Reynolds number is rho VD over mu, which we can do pretty easily. But how do we get at the equivalent diameter? Well, we kind of already talked about that with our 4D here being equal to 2H plus W, 2H plus W over H equals W. So that is 2H plus W over H plus W equal to 4 over D. Now, equivalent diameter, we are just assuming that we talked about it here. We are assuming that the shear stress at the wetted wall will be equal to that for an equivalent circular pipe with the same average velocity, so that we can assume that this equivalent diameter is also going to be equivalent. So if we solve for D, quick math in my head, we got to flip some stuff. That's going to be 4, I'm sorry, this is HW. 4 HW over 2H plus W. So that is our equivalent diameter that we are going to need to find the friction factor. So we can go ahead and plug all of this into Python so we can solve it using the root solver. And I will see you in 1 second. All right, here we go. We're going to code up now. What I'm looking at here is also what I'm looking on here. It is the same screen. And when I'm referencing my iPad, it is just the notes that we just took. So that is what that is. So you can see that. All right, so I already threw some code in here. We imported numpy as np, and then we imported root from the root solver. And then I threw in mu, rho, and g so we can solve for the Reynolds number. And then this is from homework 3. If you see, that's where I pulled this from, homework 3. And that is the Churchill equation. So using our Reynolds number and the pipe surface roughness, we can solve for our friction factor. So that's what that is. All right, so let's get on to the coding we need to do. So from here, let me actually pull this up so you can see. So from the homework, we know that our W is equal to 0.5 and our Q is equal to 1. So we can throw those in real quick. So W is equal to 0.5 and Q is equal to 1. Our Reynolds number is equal to rho times V times D. Well, we haven't really defined that. We don't do that yet. And then what else do we need to find? Oh, theta. Theta is equal to 15 degrees, but let's convert that. So that's going to be 180. Okay, perfect. So let's define our equation. That's just going to be V as our vector. Let's take 0 out of this. Our rho is going to be equal to, Reynolds number is going to be equal to rho times V times D divided by mu. What else? F is going to be equal to the Churchill equation. Oh, I'm sorry, we need to throw in our diameter. Diameter, which is the equivalent diameter we said from our notes, was 4 times H times W divided by 2 times H plus W. It's good. Let's D. Enter. F is equal to the Churchill equation. D. I think that's what it's supposed to do. So let's return this as a vector. So from our equation, it is G minus. In parentheses, we got F times Q squared times 2 times H plus W. All of that is divided by 2 times the sine of theta and that is times H times W cubed. Perfect. Alright, let's root solve this. That is going to be EQ let's run this real quick. It doesn't like how this is below, so let's throw it above. That's an easy fix. What does it not like? Can't multiply a sequence by non-integer type of float. It's for HW. I'm going to throw this in here for now. What does it not like? I'll be right back while I figure this out. Alright, well, I think I see the problem is we didn't specify what V was. So V is equal from here is equal to Q divided by H times W. Still doesn't like that. Was that put in here? Oh, I see. This is supposed to be 0. There we go. I'm almost positive that is the correct answer. Let's just look through our notes one more time just to be sure that we put everything in right. G minus F times Q squared times 2H plus W, 2 sine theta, 3. Alright, and then let me check my key here. Oh no, it's not the right answer. What do we do now? Let's get rid of these parentheses. Yeah, because it's supposed to be 2 times H plus W, not the other way around. There we go, there's the right answer. So what the problem was there is I did 2 times H plus W, but it's supposed to be 2H plus W. So that's what that was. So we matched up with our correct answer here. We just did that little mistake right there that I created for myself. So there it is. We used the Churchill equation to solve for our friction factor, and then we used our equation that we solved to find the height of the water at the end of the aqueduct. So that is what we just solved right there. When the aqueduct is inclined to 15 degrees. So thank you very much, and I'll see you in part 2 of this homework.